Okay, here we go. We're going to do the lecture for chapter 16, which is on earthquakes today. First and foremost, what is an earthquake? Well, an earthquake is basically a vibration of the earth that is produced by a rapid release of energy. This energy is going to leave from the point of the rupture outwards in waves, and we can detect these using instruments worldwide. So let's kind of start digging into this and looking at it. Now, earthquakes are produced along fault lines. Fault lines, as we talked about with the structural geology, is a break in the crust where there's been movement or displacement. Okay, so this is where the motion has actually occurred. Generally speaking, most of these locations are also very well explained by plate tectonics because most of the active fault systems in the world happen to be at or near plate boundaries. If you look in your book, on page 391, at the bottom of the page, there's a couple of illustrations, one showing the Aleutian Arc, the other one showing the western coast of the United States, and you can see the concentration of earthquakes in those areas. This happens to be a transform boundary on the east or the west coast of the United States. The Aleutian Arc is a subduction zone boundary. So again, we can follow this through. So how does this work? What is causing an earthquake to happen? This gets into an idea put forth by a gentleman by the name of H.F. Reed, which is called the elastic rebound idea, or elastic rebound hypothesis. Basically, the idea is that rocks on either side of the fault are deforming by tectonic forces. They're deforming by bending a little bit. And this bend is going to store elastic energy. So we're not exceeding the elastic strength of the material or the elastic limit of the material. Now, generally speaking, what is keeping the rocks from moving or the fault from moving is going to be friction. So like if you push your knuckles together and then try to move, you can, depending on how strong you're pressing in, you increase the amount of friction and it becomes harder to actually cause slippage to occur. So slippage is going to occur then when the weakest point of the fault line finally reaches its elastic limit and begins to fail. This is usually called the rupture point or the focus of the earthquake. Now, generally what will happen to kind of demonstrate this in the long run is rocks are going to bend like that in a subduction zone and then pop. And that popping allows that bending to release its energy. So the rock springs back to its original shape in an elastic rebound. And so we get this energy then that pushes outwards from there. Generally speaking, where the friction along the faults is greater, we tend to see larger earthquakes. Where the friction in the faults is lower, we tend to see smaller, more frequent earthquakes. Okay? Now, earthquakes do not usually happen in isolation. They sometimes are followed by smaller earthquakes that we call aftershocks. Sometimes they're actually preceded by other earthquakes that we call foreshocks. Sometimes they occur in clusters that move along a fault line system that we call an earthquake storm. So we kind of have to take a look at the system and see what is happening over time to really identify what was the main shock, what ended up being a foreshock, what ended up being an aftershock. As we've touched upon before, the most studied fault zone in the world is probably the San Andreas Fault, for a number of reasons, not to mention the fact that we've got major cities built on top of and or next to it. Generally speaking, the displacement there occurs in 100 to 200 kilometer long segments. Some areas are moving very gradually with there's fault creep going on, so they tend to have very, very small earthquakes, almost imperceptible. Other systems can store energy for several years to hundreds of years before they activate. Generally speaking, again, this is a strike-slip motion, so the material is trying to go past each other, not up or down. Generally speaking, you see larger earthquakes, or sometimes great earthquakes as they're called, on the fault, depending on the section, every 50 to 200 years. So when we look at the study of earthquakes, we call that seismology, especially the earthquake waves. Believe it or not, this study actually goes back over 2,000 years at this point. Your book, I don't think, your book doesn't have it, but an older book that I've got does. The Chinese actually had machines, artifacts would be a better term, that would tell them when an earthquake had occurred and basically where the earthquake occurred within a certain degree of reasonability. Let's see if I can find a copy of this picture. The way it worked is, imagine there it is. It's going to be hard to see because they shrunk the picture down in this book. There it is. So this figure, you have 8 dragons on basically a jar, and below each dragon is a frog with its mouth open. Each dragon holds a small ball in its mouth. The interesting way that this actually was engineered, and it's a fascinating piece of engineering for something that was done 2,000 years ago, is that when an earthquake occurred, the dragon facing the direction the earthquake occurred in would drop its ball. All the other balls would remain in place. So it's some very, very fascinating engineering. But this was useful back then because this during the Warring States era of China, where you had multiple mini kingdoms constantly at war with each other, and a good time to attack is after an earthquake. If you were devastated by an earthquake, your enemies would attack you. If your enemy was devastated by an earthquake, you would attack them. Today, we have instruments that we call seismographs that are actually able to record these seismic waves as they transmit through the earth. Generally speaking, they can look something like this in simplicity, where you have a recorder weight that's on a spring, and then as the ground moves up and down, it draws a line on a rotating drum and tells you whether or not it's moving. Generally speaking, we actually have these systems that measure in 3 different axial directions: X, Y, the Z direction, the X direction, and the Y direction. So that way we can measure the 3-dimensional movement of the ground. Generally speaking, the recordings that are recorded are also called seismographs. So the plot that's generated and the machinery are both called seismographs. Now, let's talk about what they're actually recording. They're recording the movement of the earth as the energy is passing through it. So we need to talk about what the different waves are. We're going to work backwards on this, I think, because it's a little bit easier. There are 2 general types of waves that you can have from an earthquake in simplicity standard, but not in what we're going to be requiring for understanding for our class. We have waves that travel through the surface of the earth, and we have waves that travel through the body of the earth. So the first category we'll touch on are the surface waves. These travel only in the outer portion of the earth. They are very complex in terms of their motion. You can be up, down, left, right, side to side, back, forth, and diagonally all at the same time. So they have very complex motions through them. They also tend to have the largest amplitude in terms of the movements that are going to be occurring, so that they really tend to be very destructive waves. They also tend to have the greatest periods, which is the time between the peaks of the movement. So if you think about back to when we were talking about waves in the ocean, how frequent are they? They tend to be less frequent, but they're moving more, so that also makes them more destructive. Sometimes these are referred to as L waves, which can stand for long wave or love waves. Either case, they're waves that hit last, and these are the ones that actually cause the vast majority of the destruction. We'll see a seismograph here in a minute. I've drawn one up just for illustration purposes. The other types of waves are the body waves. Body waves are the waves that move through the interior of the Earth. Now, unlike the L waves, the body waves are less complex in their nature of motion. These come in two different types also. The first is what's called the P wave, or the primary wave. Some people would also refer to it as a push wave. This is a wave of compression and expansion that moves through the material. It is exactly the same as sound. Okay? When I'm talking, the sound that I'm creating is a series of pressure waves that then go out to the microphone of my iPad, get converted into electronic signals that then get reconverted as you're watching this into a series of pulses from your speaker, which create a series of compression waves or pressure waves through the atmosphere. Now, the interesting thing about these compression waves or push waves are that they will travel through any medium. They travel through solid, they travel through liquid, they travel through gas. The interesting thing about it is the more dense the material is, the faster they travel. This is why you can run the experiment. Do this, don't do this for real, but you could run the experiment where you go out to the train tracks, with a friend, your friend has a hammer. Your friend walks 100 yards down the tracks. You put your head on the tracks with an ear to the track. Your friend then hits the track with the hammer. And you can actually see that, or hear, that you will hear the hammer hit in the ear that's on the track before you hear the hammer hit come through the air. So the sound travels faster through a solid material than it will through a gas. We can use this to our advantage, which we'll see later, into helping us identify the features inside the interior of the Earth. Generally speaking, when we're talking about P waves, they are also the fastest of the waves. So when an earthquake happens, the first wave that a sensor is going to detect is going to be the P wave. And they travel on average about 1.7 times faster than the next wave, which is the S wave, or the secondary wave. We can also call it an S wave because it has a shake motion. If you've ever been out to the yard and you have a hose that you're pulling, and the hose gets stuck on something, you whip it up and down like that. This isn't long enough to get a good one going, but let me see if I can. You shake it like this, and what you're doing is you're getting a side-to-side motion that's translating. It's a shake motion, so the motion is at right angles to the direction of travel. This actually temporarily changes the shape of the material that it's moving through. It will only travel through a solid. It cannot travel through a liquid or a gas. And as we already demonstrated, slower than the S wave or the P wave. So if we look at a seismograph that's drawn up, and this is not very well done, this would be the P wave, this would be the S wave, these would be the L waves. So we can see that there's a temporal difference between when these are arriving. This difference increases as the distance from the location of the earthquake to our recording station also increases, and that's something we'll talk about here in a little bit, but it's something that we can use. So, how do we go about identifying these things in terms of the different terminology? This is something I'm going to ask you on the final. So, I want to draw this out so you can see it. So if I have the surface and a fault line. What we end up with is we have the surface here, we have a fault line here, and we're going to cause a rupture of the fault system at this point here. This is what we call the focus, the point where the rupture actually originates or occurs. This is where the earthquake waves actually originate. Above it is the epicenter. The epicenter is the point on the ground that is directly above the focus. So if you ever listen to a news report carefully about an earthquake, what they'll sometimes tell you is that the epicenter was in such and such location and the earthquake was X number of feet or miles deep. That actually will give you the idea of where the focus was. So if they say the earthquake was 75 miles northeast of San Diego, and it was 5 miles deep, that tells you everything you need to know to figure out where that rupture actually occurred. Now, we can locate the epicenter very carefully and very quickly by just having the location of the earthquake recorded by 3 seismograph locations. I shouldn't say the location, by having the seismograph of the earthquake recorded. Because we know the speeds of travel between earthquake waves and how fast they generally travel in the crust, we can actually figure out, based on the timing of the earthquake, how far away the earth between the two waves, the S wave and the P wave. We can then figure out how far away that was. So, if we do that, sorry about that. If we do that, we can actually create a circular radius around our station that says the earthquake happened somewhere here. So if we do that in practice, it can look like something like this. If I have 3 stations, I'm going to label them A, B, and C. And let's say that A says the earthquake happened in a radius like this, okay? And B says it occurred in a radius, I got to get that radius. Like this. What we see is that we have 2 intersecting circles. Those 2 intersecting circles give us 2 possible locations for the earthquake. So we always have to have a third for this triangulation. And if C said it had a radius of this, then we can see, okay, where the 3 circles intersect, that's where the earthquake actually occurred. So as long as we have 3 seismograph stations sufficiently separated distance, we can tell where an earthquake occurred anywhere in the world, literally in minutes of it happening. Now, we can also look at this in terms of the travel graph. There is a graph system that we can show. This shows it here in your book, page 388. So here it's showing 3 different seismographs and showing the separation between the wave fronts for the P wave and the S wave at different times. So you can see how those travel out, and then we can use that chart to actually figure out the distance to a location. Now, generally speaking, 95% of earthquakes occur within what we call earthquake belts. These are areas that are going to be relatively narrow. They wind around the globe. Very specific belts are more active than others. The major ones are the Circum-Pacific Belt, sometimes referred to as the Ring of Fire, the Mediterranean Sea region, going from basically all the way through Iran, in the Middle East, into the Himalayas, and then the Oceanic Ridge Complex. So we can see how these earthquakes are plotted out around the world, following basically the convergent and divergent boundaries of the plates worldwide. Now, where do earthquakes occur depth-wise is a little bit different. Generally speaking, most earthquakes occur anywhere between 5 to 700 kilometers deep in the crust. Generally speaking, once you get below 700 kilometers, the pressure and temperature regimes that are present mean that the crust cannot deform brittly anymore. So you don't see earthquakes below those depths, typically speaking. Now, we do classify earthquakes as shallow, intermediate, or deep based on how deep they occur. If it's within 70 kilometers of the surface, we call that shallow. If it's within between 70 and 300 kilometers, we call that intermediate. And if it's deeper than 300 kilometers, we tend to call that a deep focus earthquake. Now, this actually is very important information for us because it creates something called a Benioff zone. And what we can do with this is actually look and map where subducting plates are. Because realistically speaking, most of the time, the earthquake is occurring within the subducting plate once it's below the overriding plate. And so what we can see, and I don't have a good illustration of this for you right now, I don't have the right book for it, is if we map the location of earthquakes in terms of the location of the epicenter and color it based on the depth, what we see is that the depth changes with distance away from the subduction zone. And what we can see with this is how fast or how steeply the plate is actually subducting. So it's interesting to see that the earthquakes right at a subduction zone tend to be shallow. Get a little ways off the subduction zone, they tend to be intermediate. And the further away you go, the deeper they get until you get to the 700-kilometer cutoff. So this helps us understand the nature of how different plates are subducting. And it's the Wadati-Benioff zone, now that I remember it. So we can actually do this worldwide, and we can see these patterns. Now, how do we measure an earthquake? What measurement do we use? Well, over the years, we've used two primary sets of scales. An intensity scale, which is based on the amount of, or degree of shaking that occurs at a given location, or a magnitude scale, which is basically the amount of energy that's released. Each have their pros and cons. Intensity scales, typically the most common one is something called the modified Mercalli intensity scale. This was developed using California building standards as its standard. But the major drawback with this is that the amount of destruction that you see is not necessarily a true measure of earthquake severity. In part, this can be because you have differences in building codes. A lot of times in the world, you can tell the difference in a country's building codes by looking at the earthquake damage and then realizing what that's going to mean about the nature of the population of that country in terms of its overall wealth. Generally speaking, the richer a country is, the more restringent, the stronger the building codes are going to be, therefore the less damage they're going to receive. Areas that are poorer tend to have lesser building codes, and therefore they're going to see more damages during an earthquake. Now, this makes the intensity scale very hard. There's also some other factors we'll talk about here in a little bit that make intensity a difficult one to use. Magnitude scales, on the other hand, measure the idea of the amount of energy that's released. So the Richter scale is the most common one that's used today. It was created by Charles Richter in 1935. It's based on the amplitude of the largest seismic wave that's recorded. It also is set up so that it accounts for the fact that the amplitude is going to decrease with distance. Again, if we think of an earthquake energy as sound energy, the closer you are to the source, the louder the source sounds. But if the volume at the speaker remains the same, the further away you get, the quieter it becomes. And this is because the amplitude is being spread out as the wave spreads out. The largest magnitude was recorded on a Wood-Anderson seismograph, and that used to be a 9.8. We've now seen bigger. Magnitudes generally that are less than 2 can't be felt by humans. You actually have to get well into the 3s for it to be felt by most people. Each magnitude of the Richter scale, now this is where it gets to be really interesting, because it's basically a logarithmic scale. So each magnitude corresponds to a 10-fold increase in amplitude. So the amplitude gets 10 times bigger with each one-digit number. And the energy increase gets 32-fold larger. To put this into perspective, if you've watched Godzilla, okay, the nuclear bomb test in the 2014 Godzilla was the Castle Bravo H-bomb test. That nuclear weapon, okay, to put that into perspective, the magnitude 9 earthquake that hit off the coast of, I believe it was Indonesia in 2004, that earthquake was releasing 32,000, let me say that again, 32,000 times more energy than the first H-bomb test, the Castle Bravo test. We're talking about very, very significant amounts of energy during these systems. Now, there have been a number of systems that have been developed over the years. One that's coming up now is the moment magnitude scale, which is developed in part because none of the Richter scales really adequately estimate large earthquakes. And so one of the things this is looking at is the amount of displacement that occurs along a fault. It's calculated using the average displacement on the fault, the area of the rupture surface, and the shear strength of the fault block. It's gaining acceptance among engineers and seismologists. The only problem with it is that realistically speaking, getting out and making those measurements, not the first thing anybody's going to be thinking of in a response to an earthquake. We're really going to be more focusing on the human aspects of it. So speaking of the human aspects, let's talk about what causes the damage, what causes the destruction. Generally speaking, there are 4 things that really add to the damages caused by an earthquake. The intensity. How strong is it shaking? Okay, so the stronger something is shaking, the easier it is for it to get broken. The duration of the vibrations. The longer something is vibrating, the more likely it is to suffer damage. This plays into the nature of the materials that the structure is actually sitting on. Turns out, if you had a choice, you want to be on a solid rock foundation rather than a sediment-based foundation. And the reason for this is very simple. In solid rock, the energy just passes through and that's it. In sediments, that energy can actually start causing the sediments themselves to vibrate, and they can actually amplify the amount of vibration. So you actually get more shaking, stronger shaking in sediments than you would in solid rock. And then there, of course, is the design of the structure. That gets back to the building codes. So all of this has to do with many different factors. And this is why as earthquakes become more recognized in certain areas, we have moved to building more and more earthquake-proof buildings or earthquake-resistant buildings. In fact, some of the larger skyscrapers in Japan, in parts of Indonesia, China, and California are actually physically separated from the ground. They actually sit on these plates that will actually allow them to, or springs that will allow them to wiggle back and forth, dampening the amount of energy or shake that actually goes into the building. Now, generally speaking, when an earthquake hits, good rule of thumb is the area within 20 to 50 kilometers of the epicenter is going to experience the same amount of ground shaking. And it's also usually going to be typically the most ground shaking. However, soft sediments, again, they generally amplify the vibrations more than they do in solid rock. So therefore, it's possible for regions further away from the epicenter to experience more damage than areas near because of this effect. This effect also can cause liquefaction. There's one of the videos I want you to look at after this deals with that. It shows you some liquefaction occurring in a Japanese park during the 2011 earthquake. But basically, unconsolidated materials that are saturated or close to saturated with water can actually become and behave like a fluid if enough energy is put into them. Even dry materials, if you put enough energy into them, can act like a liquid. Generally speaking, though, when we're dealing with natural situations, you're dealing with water-logged sediments, and therefore they can become unstable. There are pictures that you can see of buildings in Mexico City where the whole building just kind of fell over onto its side, intact. And what happened there is one side of the foundational area of the ground became liquid during an earthquake, and the building just basically rotated over. We can also get seiches. Seiches are the rhythmic sloshing of water back and forth within a reservoir or a lake or even a pool. Easiest way to explain this is when you were a kid, don't deny this, you all did it, we all did this. There was that point in time you're in the bathtub and you start moving back and forth, and you found you could get the water to move back and forth and trying to see how close to the edge of the bathtub could you get it without it spilling over. We've all done that. It's basically a siege type of form where you're rhythmically sloshing the water, and it can, if you do it just right, it can build on itself. Then there are tsunamis or the seismic waves. These are mistermed by many people as tidal waves. That's a completely different thing. But these tsunamis result from a vertical displacement of the sea floor. So generally you have to have a significant displacement of the floor. It has to be in a shallow enough column of water so that all of the water moves up instantaneously. Generally speaking, in the ocean, in the open ocean, these things are very flat, hard to see, maybe a meter high, and they have wavelengths of kilometers. So they really aren't noticeable in the open ocean. When they get near to shore, they can pile up and exceed 30 meters or 100 feet in height. Super destructive. Several of the videos I've put links up for are about tsunamis, just to give you the ability to understand and get a feel for what these events are like without actually being there. Of course, we can see land subsidence or landslides during an earthquake. Earthquakes can actually trigger mass wasting events. And then fire. The 1908 earthquake in San Francisco was destructive because of fire, because you had natural gas lines. Natural gas lines get disrupted, they're broken, you've got gas going out, a little bit of spark from something, you've got a fire. Well, during an earthquake, if the gas lines are getting broken, the odds are the water lines are getting broken, so you're not going to have water to fight those fires to begin with. So, towards the end here, can we forecast earthquakes? The answer is sort of, kind of, maybe, not really. We can do short-range predictions, which is the goal is to try to do a warning that says, hey, you know, we got a location magnitude within a narrow time frame. We're researching this. There's some things that are working for it, but like volcanoes, fault systems are, again, very individualistic. So it takes a long time to develop the characteristics of that fault to understand it. And then there might be things in there that you don't even know exist that can play a role. Right now, we're concentrating on things like uplift, subsidence, strain, and rocks. Currently, no reliable method whatsoever for this. Some people are looking at animal behavior because there is at least anecdotal evidence of animals predicting earthquakes. There seems to be some degree of real science behind this. We're still trying to study that. Long-range forecasting, that we can do. That's more like a probability. So we say that, you know, there's an X% probability over the next 30 or 100 years that a large earthquake is going to occur in this fault. We can do that. Not very useful, unfortunately. But we can use that using historical records, paleoseismology. It helps us to inform things like the building code and the land use plans. But it's not going to be, hey, don't be in your house on April 15th, 2023 because in San Diego because there's going to be an earthquake that day. Doesn't work out that way. And then again, as I said a couple of times, earthquakes are evidence for plate tectonics, not only because of the good fit between plate tectonics model and the global distribution of earthquakes, the connection between the depths of earthquakes and the subduction zones is also good. It's just all around a good fit. Now, after this lecture, which is a relatively shorter one tonight, 37 minutes at this point, I did post up links to YouTube videos looking at several different tsunami events recorded by real people during the tsunamis. Also, the Seach video the liquefaction video and building swaying. Try to give you an idea of what it's like to be in an earthquake event without actually having to be in one. The tsunami videos, please keep in mind, when you're seeing people getting hit by the water in those, you are watching people die. No way around that. But it gives you an idea of what's going on in those moments. And it is surreal to watch and suddenly see the ocean just kind of going out away from the beach, and then to see a large foaming structure of a wave then riding in and being bigger than anything else that's out there. So with that, I'm going to leave it here, about 38 minutes, and I'll talk to you guys later.